Okay, yeah.
The hydrogen gas, the mass might be 3 and to 2, right? This 2 means you have a
Oh.
this one and this
Oh,
one.
I see. Okay.
And
Yeah.
this 3 is actually D2 and H1,
Okay.
right?
Yeah. Okay.
Ideally you want to measure this ratio, but
Okay.
sometimes you got this guy.
Oh, I see. Oh, okay.
Still the same ratio,
Right.
and you don't want that.
Okay.
There-
Because that doesn't really tell you any information.
No.
Because it's all H's. Okay.
Right. So this called a H3 factor.
Got it. Okay.
Each day when you analyze hydrogen isotope, each day you have to check out the H3 factor below some value. I forgot that one.
And then do you
It's supposed to be below
remove that?
10.
Okay.
I think it's parts per million or something.
Yeah,
like
I
that.
forgot the unit.
Yeah,
Yeah.
I've got the unit.
Is this like excess deuterium?
Huh?
In the meteoric water line, deuterium, excess deuterium.
This is deuterium.
Yeah,
So
so the
you have-
H3 factor is measuring deuterium plus H has the same mass as 3
Hydrogen. One.
hydrogens. So you're trying to decrease the false signal from the 3 hydrogens because you're wanting to look at deuterium. So like when the gas gets inside the source, it's being attacked by a electron machine gun. So like you enter a room and so you're gas and you enter this room and you're getting shot at by electrons. So some of your electrons then fire off and you become ionized. That happens to all the gas in there. So sometimes you're getting excess hydrogen that becomes ionized instead of the deuterium, and that comes together and goes through. So the way the source is organized, there's a box and a trap, and the electrons are flowing through and getting captured, and you're it's easier to see when the source is out, but there's 2 magnets that give everything a spin, and because everything's being ionized, you have a statistical probability of what becomes ionized and what gets trapped in the trap and what actually comes through the source to be collected by the Faraday cups.
So you are
And the
refer-
H3 factor is shows you how much of the false signal is getting through. It's always going to happen, but it shows you the amount, and you want it to be below 10.
So when you
this
do
is-
that number, do you subtract it out of the signal, or do you it's just information that you know? And
ISO that automatically subtracts it and calculates
okay,
it based on statistics.
got it.
And the amount of hydrogen that gets through, I believe I'm saying this correctly, is kind of dictated by these values.
Okay.
So this is the amount of, I'm just going to use the word energy, even though that's fake.
Okay.
The amount of energy, like electricity that's going into the source that's controlling all these parameters. So if you have
Are these like representative of physical things that are happening in the?
yes.
Okay. Like each line here,
Each
emission
line,
is
yeah.
a physical piece, trap is a physical piece.
Emission is the amount of amps that are going to it.
Okay. Yeah.
The energy for the electron cannon. The trap is the voltage. Do you know what voltage?
That's this guy.
Yeah. So voltage is a potential of things, right? It's kind of like potential energy. The volt, like if it's describing like the difference in electricity, I guess, from one part to another.
Okay.
So this is saying that there's a 40 volt difference between 2 parts of the components of the source. So the higher the trap voltage, the more I believe it's the more positive energy that the trap is getting. So the excess electrons get sucked up and trapped in the trap.
Okay.
So if and the electron energy is the amount, I think that's the amount of bullets from the,
Sure.
and the extraction is the energy that it takes to extract the the ions through the source.
So that's represented as a percentage. Is that saying like it takes 92%
of
its energy?
I think of the amount of emission, I think, but I'm not positive on that.
That makes sense, I think.
And everything, I'll explain everything below that in a second,
Okay, yeah.
as best as I can.
Sure.
I believe it's either the electron energy or the extraction. It's probably the electron energy. When you're analyzing hydrogen, I think that has to be lower to decrease the amount of bullets that are firing, to decrease the amount of H that you're making.
So the higher electron energy you have so much bombardment of electrons that you're breaking apart some of the deuterium, and that's how you get.
Yes, I believe, and that's why you're getting too much H.
Right.
3 H's. Yes.
Yeah.
Not
Okay.
tritium.
I think it's coming together in my head a little bit. Yeah. Okay.
I think about this stuff so infrequently that I can't remember all the parameters, but that's like
okay.
generally on how these things go. X focus to the Y deflection, that is these physical plates.
Oh yeah, we were
here.
talking about that a little bit.
Yeah, so if you see these little nodes, these,
Okay.
there are leads that attach to them, and that gives them electricity to kind of shape and force that electron beam through the source. So there's a slit in there,
Okay.
and the electrons are being and the ionized gas are being forced through, and these are given electricity to kind of like move. So you'll see there's a slit in this direction, and there's a slit in that direction, and that makes it tunes the guitar string of the ion beam through there. So all these slits are kind of like moving in different ways, not physically, but with electricity,
Okay.
to optimize that beam through the slit, so it gets to the Faraday cups.
So it's not physically opening and closing the slit size. That's not what you're saying.
No,
It's
electronically opening, moving, because it's an ionized beam.
right.
So all these holes,
Okay.
there's
Oh, so it's not passing through these.
no, it's that
slits.
slit.
Oh,
They're
it is
passing through the slit.
Okay.
These 4 holes, these ceramic posts go through those holes, so
Okay,
they're not
gotcha.
moving.
Okay. Okay.
It's very much static in there. It's just receiving an electrical field that tunes it. Well, you could in some way think about this, I guess you could think about music or any instrument that needs to be tuned, like this needs to be tuned as well. And that's
Interesting. Okay.
These are the guitar pegs on the guitar that help
Okay.
get everything in tune. When it's not in tune, the shape is bad and the intensity is bad. It doesn't make its
So
way
if this all looks
completely.
weird, then you might like mess with some of these numbers.
Yeah.
Okay.
So it's usually the intensity. So you want even though an electron beam is getting into the cups, this will maximize the intensity.
Okay.
Intensity is one component. The other component is linearity.
Okay.
So the higher the intensity, usually the worse the linearity is.
Oh,
So
okay.
you're trying to find some sort of balance
Sure.
between linearity and intensity.
Got it. Okay.
So this is great for CO2, but when you start messing with hydrogen, then like there's extra components that go into the peak
Right.
shape and
Okay.
yeah.
Got it.
It's problematic for hydrogen.
Yeah.
It's more
So-
difficult to analyze hydrogen.
Okay.
So this intensity is the active portion of the ionized gas, right?
The intensity is the voltage that's received by the Faraday cups of the ionized gas.
Okay.
So the only gas that's making it to the cups is the ionized gas.
So the other portion, not ionized gas, we have to subtract it, right?
Well, maybe everything isn't the right term, but like everything is getting ionized in the source,
Okay.
but not all the ionized gas is actually passing through the source to get to the Faraday cups. Because like if you like you're generating gas, like the gas is coming out of the cylinder and it's going into the conflow, and it's constantly flowing, but it's flowing into an open cup pretty much, and the capillary comes down to like sniff that, and then the capillary then brings the gas into the source. When it's in the source, not all that gas is actually ionized and brought through. So some of it is not ionized, but everything that makes it to the cup is ionized. Otherwise, it would never get picked up by the magnet current to get there. So there's some parameter in the diagnostic window that you can click on, and it'll tell you how much of that gas is ionized. There's a limit. It's something like 800 molecules, 800 molecules. Let's say maybe out of every like 10,000 molecules, 800 are ionized. Something like that. It says it in the book.
Okay.
I don't remember. Yeah. It's interesting how it works.
Yeah.
And it's all based on, and it's all statistics, right? Like,
Yeah.
even if it's not working correctly, as long as everything's treated the same, it doesn't matter. Like standards, right? It doesn't matter if your standard was off by 1 per mil from the international standard. It doesn't matter because it's as long as it's consistent.
As long as everything is off on board.
Yeah. So it's like the precision versus accuracy, right? Like that thing is built for precision, not built for accuracy.
Yeah.
So if you're like way off the target but it's super tight, you could adjust the scope to bring it back, and that's what the international standard was.
Oh, so that's how you describe this guy? Is that it's built for precision, not accuracy?
Yeah, this is
okay.
all precision.
Interesting. Okay.
You need I don't know how wrong I am with this either. If you want something that's accurate, you have like the mass spectrometers the size of this room. They're large mass spectrometers that are used for accuracy.
Yeah. Those are the accurate ones.
My brain doesn't function with the I don't know how you come up with accuracy. I have to sit down and think about that for a really long time. But yeah, these and the 253 are built for precision.
Okay.
Probably way more information than you needed to know, but
No, it's good. It does. Yeah, it feels like.